Another source of energy for us is nuclear reactors. So in case of nuclear reactors, we have a reactor core where we have nuclear reaction taking place, that is controlled nuclear reaction which is taking place. So there are many things which are required in a nuclear reactor. The first one is the core of the reactor. After the core, we need to control the amount of neutrons released. For that purpose, we have the control rods. Control rods are pushed into the core and withdrawn depending on the number of neutrons or depending on the amount of energy that needs to be released. If you need a larger amount of energy that needs to be released, then we will withdraw the control rods from the reactor core, and if you need very less amount of energy, then what we do is we insert the control rods into the reactor core. So the control rods, they absorb the neutrons and reduces the number of fission reactions, thereby reducing the amount of energy released in the nuclear reactor. And then we have the moderators. The neutrons released during a nuclear reaction or nuclear fission are moving at a very faster pace. So we need to reduce the speed of this. For that purpose, we have moderators. So we need a slow moving neutron for the continuation of the chain reaction. So the uranium-235 needs to be bombarded by a slow moving neutron. For that purpose, we have the moderator which reduces or which absorbs energy from the fast moving neutrons and reduce the speed of the neutrons. And then we have the reflectors. So the core is surrounded by the reflector. We provide reflector so that the neutrons which escapes from the core can be reduced. And after the reflector, we will have the pressure vessel, where the pressure vessel is covering the entire core of the reactor. A pressure vessel will be able to contain large amount of pressure from inside. And then after that, we have the containment structure. So containment structure will be made up of iron and cement. So generally its thickness varies from 1 meter to maybe around 5 to 6 meters. So that containment zone is provided if there is any escape of nuclear, the neutrons or gamma rays or X-rays which are produced during the combustion, during the nuclear reaction. So those rays needs to be, or those radiation needs to be contained within a zone. Those radiation needs to be absorbed. So for that purpose, we have the reflector and the pressure vessel, and if by any chance the radiation leaks out of the pressure vessel, then that will be contained with the help of the containment structure. So containment structure generally made up of iron and concrete. So inside the containment structure, there will be very limited access for the workers, and whenever they are going inside the containment zone, they have to wear suits which will absorb the radiation and reduce their exposure to the radiation. And there will be time limit within which they have to come out. If they are exposed too long, then it may be harmful for the person entering the reactor core. So for that purpose, containment zone will be well guarded and access will be given to very limited people. Outside the containment zone, you will have the control center where you will control the operation of all these components with the help of computers. Now let us see the working of different nuclear reactors. First reactor which we are going to study is pressurized water reactor, or PWR. So in the case of pressurized water reactor, Here we have the reactor core. So inside the reactor core we will have the fuel rods. Fuel, that is uranium-235, will be formed into small tablet like structure, and several of them will be stacked one upon the other to form a fuel rod, and a bundle of such fuel rods will be made, and that bundles will be inserted into the core. So that will be prepared outside, and then that will be inserted into the core on a regular basis. Whenever the amount of uranium-235 reduces in the core, the spent fuel will be taken out, the spent fuel rod bundle will be taken out, and the fresh uranium-235 rod will be inserted into the reactor core. Now let us see the working of different nuclear reactors. The first nuclear reactor which we are going to study is pressurized water reactor, which is also called as PWR reactor. So here in the case of PWR reactor, we have the reactor core. So inside the reactor core you will have the control rod, moderator, reflector, and whenever you are starting the nuclear reaction for the first time, nuclear fission for the first time, you need to bombard the uranium-235 with artificially created or by artificial means. So for that purpose there will be neutron emitters inside the reactor core. And then we have the pressurizer. So it's as the name indicates, it's a pressurized water reactor. So we will keep the water pressurized in the primary loop. So this is the primary loop, we will come to that later. So for that purpose we have the pressurizer. So pressurizer is nothing but it's a boiler where we are going to heat water or boil water with the help of electrical heaters. So these circles are the electrical heaters which are provided at the bottom of the pressurizer. And as you boil water or as you heat water, some of the water gets evaporated and gets collected at the top, and as you continue to heat water, then the pressure inside, the pressure of steam increases continuously because more amount of water is getting converted into steam. So that applies certain amount of pressure on the water in the primary loop. This is done because we need to keep water in liquid state in the primary circuit or primary loop. So to keep water, when it passes through the reactor core, its temperature increases, and if it is at atmospheric pressure, then the water starts to boil. So to avoid the boiling of water in the reactor core, we use the pressurizer. So in pressurizer we apply electrical energy and heat the water, and when we heat the water, some of the water gets converted into vapor and gets collected at the top of the pressurizer, and as you continue the process, more amount of steam accumulates at the top, and that increases the pressure in the pressurizer. And the pressurizer is directly connected to the primary loop or primary circuit. Because of that, the entire primary circuit or primary loop will be under the same pressure. After the pressurizer, we have the heat exchanger. So here we are not directly passing the water coming out of the reactor through the turbine. So for that purpose we are using a heat exchanger where we use water and convert a normal water which is non-radioactive. The water in the primary loop is entering the reactor core, so it becomes radioactive. But in the secondary circuit we are using a normal water which is not radioactive, and that water passes through the tubes and absorbs heat from the water coming out of the reactor core. So this is you can call this a steam generator or heat exchanger. So here the regular water enters and absorbs heat from the pressurized hot water coming from the reactor core, and then this water that is in the secondary loop gets converted into steam. That steam passes through the turbine and transfers its heat energy into the turbine blades, which converts that into mechanical energy, and that is coupled to a generator which produces electrical energy. And here, once the steam passes through the turbine, it is condensed back into liquid water. So this condensation is required because to pressurize the water again, if it is in vapor state, it requires enormous amount of energy. So condensing it back into liquid will reduce the amount of energy required to pressurize the water in the secondary circuit. And then if we reduce the pressure, if we condense the water, steam coming out of the turbine, then that reduces the pressure at the end of the turbine. So generally the turbines are reaction turbines or impulse reaction turbines. In this case, the pressure difference across the turbine is the amount of energy that can be extracted. So that increases the amount of energy extracted in the turbine. And after the condenser, we have a feed water pump. This pumps water or pressurizes the water and circulates that into the heat exchanger. So before the water enters the heat exchanger, when we can heat it to increase the overall efficiency of the cycle. For that purpose, we are bleeding or we are taking out a part of steam from the turbine. So before it completely expands and loses its heat energy, we are taking out steam. This process we call it as bleeding. So we are bleeding some amount of steam from the turbine, and that is directly mixed with the water coming out of the pump. So that increases the temperature of water. So this would be designed in such a way that the amount of steam extracted will be sufficient to reach to heat the water to reach its saturation temperature. And we need to make sure that the pressure of the blade stream will be slightly larger than the pressure of water here. Okay. After that, the water enters the heat exchanger and it absorbs heat from the pressurized radioactive hot water coming out of the reactor core and gets converted into steam, and then the cycle repeats. So here, after transferring its heat, the pressurized water, which is radioactive, enters a pump where the pump is used. The pump will help in the circulation of water into the reactor core and the heat exchanger. To keep the circulation flowing here, since everything is at same pressure, we need a driving force to circulate water in the primary loop. For that purpose, we have a pump here. So this pumps water from heat exchanger to the reactor core. So this is the working of pressurized water reactor or PWR. So here the pressurizer, reactor core and the heat exchanger, everything will be placed inside the containment structure. So all these three will be inside the containment structure. The turbine, condenser, feed water heater and feed water pump will be outside the containment structure. So the main advantage here is, since we are keeping only these components inside the containment structure, if there is any malfunction in the turbine or condenser or the feed water pump, then we can easily repair that. We don't need special equipments or special codes or special codes to be owned by the workers. So since they are outside the containment structure. So that is the working of pressurized water reactor. Another type of reactor is boiling water reactor or BWR. So here I am not showing you the turbine. Here, but this works on the same principle. Here there will be uranium-235 which participates in the fission process and releases energy. So that energy has to be absorbed by certain coolant. Here the coolant is normal water. Here we can use normal water or heavy water as coolant. So the water directly enters the core of the nuclear reactor and it absorbs heat, gets evaporated and gets converted into steam, and that steam will be collected from the top of the reactor core and that will be directly sent to the turbine. So here the major risk is the turbine will also be radioactive because radioactive water is flowing through the turbine. So it becomes radioactive and it will be difficult if there is any malfunction in the turbine or the condenser. So the turbine, condenser, reactor core, everything should be kept inside the containment zone, and if there is any malfunction then repairing that will be a tedious job. So that is the major disadvantage, but here the amount of energy the amount of energy absorbed by water will be very high because the water is getting converted into steam inside the reactor core itself. Evaporation is one of the best way of cooling any surface. So if a drop of petrol or diesel falls onto our hand, then it evaporates at a faster pace and you will feel that that area will be very cold. So because of that, evaporation is the best way of cooling which we can provide as an engineer, and that is what is happening here. So during the nuclear reaction, energy will be released, heat energy will be released, and that heat energy has to be carried away, and for that purpose we are boiling water inside the reactor core. So the water gets converted into steam and that steam will be collected at the top and then it will be supplied to the turbine. So we are providing best method of cooling the reactor core, but the major disadvantage here is since we are directly supplying the steam into the turbine, now the turbine is also radioactive and that cannot be kept outside the containment zone. So that also needs to be kept inside the containment zone, and the condenser also needs to be kept inside the containment zone, and we need to use a closed indirect contact condenser. So in this case we can use a direct contact condenser, there is no harm, but in the case of boiling water reactor we have to use a indirect contact condenser to condense the radioactive water, and that needs to be pumped back into the reactor core. Next we are going to see the gas cooled reactor. So instead of using water or heavy water as coolant, we can use a gas. Generally we use carbon dioxide, and the carbon dioxide will be pressurized to around 16 bar, and that will be used as coolant in the system. So here the major parts are, we have the reactor. Inside the reactor we will have the control rod, the nuclear fuel, we will have the control rod, and then the moderator, and then we will have the reflector, and all these things will be inside the pressure vessel, and then we have the containment structure. So we have the reactor and then we have the heat exchanger. So here we can do in two ways. We can pressurize carbon dioxide to more than 16 bar and then heat that, or made it to absorb heat from the reactor core, and then we can directly run that, or we can directly allow that to pass through a turbine to produce mechanical energy, and that can be coupled to a generator to produce electrical energy. The other way is, since the carbon dioxide is flowing or passing through the reactor core, it will be radioactive. So we can reduce the movement of radioactive elements or gases outside the containment structure. So what we can do here is, we can use a heat exchanger, or you can call that as a steam generator. So here we can have a regular Rankine cycle. The water will flow through the pipes in the heat exchanger or the steam generator, and we have the gases, very hot carbon dioxide at around 16 at around 16 16 bar pressure, and that transfer its energy, heat energy, to the water flowing inside the tube bundles. So again, the water gets converted into steam, and that steam will pass through the turbine, which converts the heat energy available in the steam into mechanical energy, and that will be coupled to a generator which produces electrical energy, and then the steam passes through the condenser. Again, here we will be using an indirect contact heat exchanger, and the cooling water will be flowing inside the tube in the condenser, and the steam will be flowing over the tubes. As the steam passes over the tubes, when the steam as the steam comes in contact with the tube surface, it transfers its energy to the water which is flowing inside the tube, and its temperature reduces and becomes liquid water, or condenses back into liquid water and gets collected at the bottom of the condenser. From there, with the help of a feed water pump, will pressurize the water and send it to the heat exchanger. And after the carbon dioxide transfer its energy to the water, it will be brought back with the help of a blower or a fan. So that will be made to circulate back into the reactor core to cool the reactor core. So thereby taking away heat produced during the fission process and transferring that to the water. And this is the working of a gas cooled reactor. Many gases can be used, but generally carbon dioxide is most preferred, and it will be pressurized so that the heat transfer coefficient inside the reactor core increases, because the heat transfer coefficient between the gas and a solid surface is very low. So here what we do is we pressurize the gas so that more gas molecules will come in contact with the fuel rods and absorb heat released during the fission process. Then we have liquid metal fast breeder reactors. So here we have a liquid metal reactor, which means to say that we use a liquid metal as coolant in this case. So here we have the schematic representation of liquid metal fast breeder reactor, but in actual arrangement there are two types of liquid metal fast breeder reactors. One is the pool type and the other one is the loop type. First, let us see the working of the liquid metal fast breeder reactor with help of the block diagram. So here we have the reactor core, and as I said, reactor core consists of control rod, fuel rods, moderator, reflector, and the pressure vessel. So everything, when I say reactor or a reactor core, it includes all those components. And then we have primary heat exchanger. So here we have primary heat exchanger, then we have secondary heat exchanger. HX represents heat exchanger. So we have secondary heat exchanger, or also called as steam generator. Then we have the turbine, a steam turbine. Then we have the condenser. Then we have the bleed pipe, and we have the feed water heater, and we have pumps to pump liquid metal as well as water in the last circuit. So if you observe this, there are three circuits here. So there are three loops or circuits in this case. The first loop is between the reactor core and the primary heat exchanger, where a liquid metal such as sodium is flowing through the reactor core. And then we have the secondary circuit, where we have the circuit is between the primary heat exchanger and the secondary heat exchanger. Again, here we have liquid metal, which is sodium, flowing through this circuit. And then we have the last circuit where we have water, and that is between the secondary heat exchanger or steam generator, and the turbine and condenser. When it comes to the working, so here we have two different loops of sodium, because as the sodium, which is a metal and that will be in liquid state because of very high temperatures, so as it passes through the reactor core, sodium becomes highly radioactive. So we don't want to take any risk. If there is any leakage of small amount of sodium to the water, then the water, since the sodium is sodium becomes highly radioactive, so that will contaminate the water, and entire system has to be shut down, and the water needs to be discarded, and fresh water has to be used. So for that purpose, we have two sodium loops, and then we have the water loop. And also the temperature will be very high in the primary loop, so we cannot directly allow water to enter that heat exchanger. For these reasons, we are using three different loops here. In the primary loop, the sodium, which is in liquid state, will flow through the reactor core and absorbs heat and then enters the primary heat exchanger. And to keep the circulation all the time, we have a pump here in the primary loop. So this pump will keep the sodium circulating throughout, the liquid sodium circulating throughout the circuit. Okay. Here it transfers its energy to the sodium, which is a non-radioactive sodium, which is present in the secondary loop. So in the secondary loop, we have non-radioactive sodium, and in the first or primary loop, we have the radioactive sodium. So here the non-radioactive sodium absorbs heat from the radioactive sodium, and then that sodium enters the secondary heat exchanger or the steam generator. Again here, to keep the circulation of sodium, we have another pump here. So this pump keeps the circulation of sodium in the secondary circuit. So now the sodium, the hot sodium coming from the primary heat exchanger enters the steam generator or secondary heat exchanger. Here we have the feed water entering at its saturation temperature. So with the help of pump, we pressurize the water, and with the help of feed water heater, we increase the temperature of liquid water to its saturation temperature. From here, the saturated water enters the steam generator, and as it passes through the steam generator, it absorbs heat from the liquid sodium and gets converted into vapor. So that steam enters the turbine and transfer its energy to the blades of the turbine, which in turn converts that into rotation of the shaft, which is coupled to a generator, and that generator produces electrical energy. And after the steam passes through the turbine, it enters the condenser, where we supply cooling water and condense the steam into liquid water. That condensed steam will be pumped, pressurized and pumped with the help of a feed water pump, and then the pressurized water will be sent to the feed water heater. Then this is the working of a liquid metal fast breeder reactor. As I said, there are two arrangements of this. One is the loop type, which is exactly similar to this, and the other one is pool type. In the case of pool type, we have a very large pool of liquid sodium. So at the bottom we will have heaters to keep the sodium in the liquid state, and inside that we have the reactor core and the primary heat exchanger. So the reactor core and the primary heat exchanger will be kept inside a large pool of sodium. The advantage of using a pool type of sodium fast breeder reactor or liquid fast metal breeder reactor is that here, if there is any leakage of radioactive sodium or radioactive material from the reactor core, that will be contained within that large pool of liquid metal or sodium, liquid sodium. If you are using a loop type, then if there is any leakage from the reactor or from the primary heat exchanger, then that will be a disastrous thing. So that is the advantage, but the major disadvantage in the pool type is we need to have a very large quantity of sodium, and that needs to be kept at liquid state, so you have to continuously supply additional heat. That is the major disadvantage with pool type liquid metal fast breeder reactor. So we call them as breeder reactor because the reaction which occurs inside the reactor will produce nuclear fuel for the next stage of reactors. So for the next stage of reactors, they produce or they breed the nuclear fuel. So for that reason, we call them as breeder reactors. And here we use fast moving neutrons for that purpose, hence the name fast breeder reactor.